It doesn't get any more fundamental than this.
The fundamental unit of the cosmos, the star.
It's how you build a galaxy.
This is like a message encoded in the galaxy. It's what allows us to see out there. Without stars, there's not much that shines.
People used to describe stars by their colors.
Yep.
For hundreds of years, they would just say, that's a red star right there, and that's a blue star over there, and that's a yellow star. They didn't know what they were talking about.
Yep.
They only just knew what they perceived through this tiny little window into space, which is our eyeball. They didn't know what that was. Mm-hmm. Eventually, somebody realized, wait a second, we're looking at black bodies.
Mm-hmm.
Stars are black bodies.
Yeah. So anything that has a temperature gives off a continuum of light.
This is actually what happens if you put like a piece of iron into a fire, and then you take that iron out, it glows. If you actually looked at it at lots of different wavelengths, the distribution of the amount of energy coming out at each wavelength would follow this characteristic curve.
And the curve of this black body spectrum looks like this. And so the only thing that determines this, the only thing that matters, is temperature.
These things don't cross, right? It kind of grows and grows along in this envelope. Kind of like a balloon, yeah.
So the sun, in which there is stuff exploding in the middle of it, gives us the same profile as a piece of iron.
Yeah.
That's the whole thing about a black body.
Yeah, so
it doesn't care what you are.
It doesn't care what you are.
black-
Your cake that you pull out of the oven.
they'll emit the same overall profile.
Black carbon in the oven, same temperature. They're both going to have the same black body curve.
The peak of this is what determines the color that you see.
Our eyeballs are sensitive to some
Very small.
for some little small little strip in here, right? So as these curves change, we'll be seeing a different sort of section of these distributions, and that's what basically changes the color. Because the relationship of the blue end to the red end of the spectrum for our eyes is what gives us the perception of color.
So we're seeing not stars of different colors, but we're seeing stars of different temperatures.
Right.
So when you go out and look at the night sky and you see a red star over there, you're seeing a cool star. You look over there, you see a blue star, you're seeing a very hot star.
So the good thing about black bodies is that once we understand them, they're very simple. That this curve that we see from a star, we can understand it very well. You can figure out the temperature of the star, and that's it. And so everything else we know about these stars comes from when they're not black bodies.
This is astrophysics at its most basic. The deviations away from it is where all the action is.
The light that is emitted in the core of the star takes 50,000 years to work its way out.
And then when it finally reaches a certain point known as the photosphere, the material in the star is thin enough that that photon makes one final leap out to our eyes.
It's opaque.
Okay.
The star itself is
So-
opaque inside.
Okay, there's a whole bunch of
It's
stuff.
ionized. It's a plasma.
It's like so hot that the electrons and protons have separated, and photons can get scattered off of these things. So it might get scattered off like this, and then it might hit another one, and maybe get scattered off some more, go in the opposite direction for a little bit. So you have a random walk. It keeps hitting things.
Yeah.
It's not a straight shot out.
The sunlight you're feeling
was created by nuclear reactions that happened way long time. But this is important, right? Because if these photons weren't bouncing off all of the material in the star, how the hell would it keep the star from collapsing in on itself?
Yeah, the star would just collapse.
That's what's doing the work.
It's this atmosphere that causes the little deviations from a perfect black body, because the photons have to make their last journey through that.
And at the end of this 50,000 year journey, that the photon
It
It's a light pole.
Sometimes it hits a light pole, exactly, at a discrete wavelength.
and these light poles are related to the transition energies of the electrons in the atoms and molecules that are in the star's atmosphere.
So you have in the center of your atom your nucleus with protons and neutrons just hanging out. Then going around you have electrons. If you can imagine them buzzing around on the outside, moving around. But when you're far away, there's very discrete energy levels. And so when a photon comes through, it might hit this electron. It's possible. And if it has just the right energy to kick it up to this level, it will do that. Otherwise, it'll pass right on by. And so all the light that comes through, on this side, everything comes in. On this side, almost everything comes out. Everything except a couple spots in here, a couple holes, which are exactly the energy to move from here to here, which are absorbed away.
And the distribution of those lines, their depths and other properties give you tons of fundamental information about the star. We can tell you by a detailed study of the exact positions of those little divots We could tell you the amount of iron, the amount of sodium, the amount of potassium, the amount of, in some stars, the amount of titanium oxide or carbon monoxide that's in the star's atmosphere.
This is how we can tell what elements are in the cosmos, because each element has its little electronic fingerprint.
So you can define me uniquely by my DNA, and you can define a star uniquely by its combination of chemicals, temperature, and age. And just like you can sequence my DNA and tell me who I am, what color my eyes are, and what texture my hair is, you can read the spectrum of a star and completely characterize it. I can tell you everything about the star, what it's made out of, how massive it is, how long it's going to live, and if it has a family of planets.
The fact that we understand these lines and can do work with them is what took astronomy from being counting and figuring out people's horoscopes into a legitimate science, to where you can make predictions and test them.
It's hard to conceive that really these little atoms in our bodies were actually forged together because of the intense pressures inside of stars that are hundreds, thousands of light years away.
Yeah, the universe started as hydrogen.
This is all there is in the universe.
Yeah.
Right.
Hydrogen, helium, and metals.
Right.
Tiny amount.
And the metals come from the fusion going on in stars, turning these really light elements into heavier elements over time.
So when the star is done fusing all of the hydrogen and helium into heavier stuff, some of them explode, some turn into planetary nebulae, and then they cough that newly formed heavy elements out into space, where it gets mixed up with other interstellar stuff.
And then new stars form the stuff that the old stars just coughed up, so then you get stars that have a little bit of heavier elements in them. And then over time, you get more and more stars that have heavier and heavier.
And now that you have iron and carbon, all these other metals in the interstellar medium, planets can form out of this.
The evolution of the universe.
Yeah, I have a titanium ring. This
Amazing
ring
network.
wouldn't be here if it weren't for the deaths of millions of stars. So that's kind of cool.
I'm made of carbon. Yeah,
There you
I
go.
wouldn't be here.
And then
So
this-
we're like literally made out of star stuff.
yeah.
Now we can look up at stars and we have a physical understanding of what we're seeing. And so one of the biggest open questions in astronomy today is the almost universal mass distribution that we observe for stars throughout the entire galaxy. So the number of stars, the function of mass, can be well approximated by the mass of the star raised to the minus 2.35 power. Why does it look like that? Well, it's basically nature's way of waving a flag and saying, check it out. If you can decode this rule, then you understand something profound about where we came from and how it all happened.
I mean, we come from stars, right? This is us. And we're broadening that context.
And it all starts with getting people interested in it from the get-go. Taking your child outside, looking up at the stars, and they might ask you, why is that star red? What is it made out of? Where does it come from?